Today I'm doing Chapter 2, Functions and Graphs. Section 2.1 is the modulus function. Solve the modulus of 2x minus 6 is equal to 10. Alright, so 2x minus 6 has to either evaluate to 10 or negative 10. And if it evaluates to 10, then x is 8. And if it evaluates to negative 10, then x is 0. And so the solutions are 0 and alright, let's try again. Right, we have to think of a more efficient way to say this aloud. Modulus of 2x minus 6 is equal to 10. So 2x minus 6 equals 10. So 2 is 8, so x is 8. Or 2x minus 6 is minus 10. So x is minus 2. So minus 2 or 8. Minus 2 or 8 are the solutions to modulus 2x minus 6 is equal to 10. Modulus 3 minus 7 plus modulus negative 2 times modulus 5. Modulus 3 minus 7 is 4, and modulus minus 2 is 2, and modulus 5 is 5. And thus it becomes 4 plus 2 times 5, which is 14. So 14 is the answer to modulus 3 minus 7 plus modulus negative 2 times modulus 5. State the range of f of x equals modulus x minus 3 all plus 2, or x, for real values of x. Okay. So we visualize that f of x equals modulus x. Looks like the characteristic V shape. And by subtracting 3 from the argument, it translates 3 units to the right. The cusp moves 3 units to the right. And by adding 2 to the whole function, the cusp moves 2 units upwards. Meaning that the range should be that x is greater than or equal to 2. That's the range. The range of f of x is greater than or equal to 2 for f of x equals modulus x take 3 all plus 2. solve modulus x plus 1 equals 3x minus 5, rejecting any invalid root. Alright, so first we're going to say that x add 1 equals 3x minus 5. In which case 2x is equal to 6. In which case x is equal to 3. And that clearly works by substitution. But then we have to reject invalid roots. Alright, so we're going to visualize modulus of x. Visualize it horizontally translated 1 unit to the left. And then we're going to visualize 3x plus 5. And we can see that it passes through the y-intercept at 5 with a gradient of 3. Okay. Alright, so we can clearly see that it only intersects it exactly once, and that would be 3. So 3 is the root of modulus x plus 1 equals 3x minus 5. How many real solutions does modulus x equals x squared have? Alright. So it should have 3 real solutions, namely -1, 0, and 1. Okay, section 2, functions and mappings. State the range of f of x equals x squared minus 4x plus 7 for x belonging to the real numbers. State the range of f of x equals x squared minus 4x plus 7 for x belonging to the real numbers. Okay, so we have to find the minimum of this function. So the way we're going to do that is we're going to find the line of symmetry, which is minus b over 2a. And thus in this case it's going to be 4 over 2, which is 2. And then we're going to substitute 2 into that quadratic function. So we're going to have 2 squared minus 4 times 2 plus 7. So 4 minus 8 plus 7, which is 3. And so x will be greater than or equal to 3. Or rather, f of x will be greater than or equal to 3. And that should be the range of f of x equals x squared minus 4x plus 7. Is f of x equals x cubed plus x for real x 1 to 1? Okay. So that means every input has one output, maps to exactly one output. Or does it? Is that what it means? No, that's not quite right. What it means is that an element of the range is only mapped to by one element of the domain. Alright, and so the function is f of x equals x cubed plus x. Okay, so we're going to visualize that. So we're going to factor it, pull out x, so we have x times x squared add 1. And the solution to that is, Alright, so let's just think about this. Okay, so when we do that, we see the solution is 0. But those are the roots, that's not a way to actually determine that. Alright, so let's see if we can remember how to actually do this. Alright, so what we're going to do is we're going to differentiate it. F prime of x equals 3x squared plus 1, 3x squared plus 1. And that has no real roots. So in other words, it's never equal to 0. What? That's strange. No, it's not strange. It's absolutely not strange. Okay, so it has... it is 1-to-1. It is 1-to-1, yes. State the largest possible domain of f of x equals 1 over x minus 2. The largest possible domain of f of x equals 1 over x minus 2. Alright, that would be the entire set of real numbers excluding 2. Next. State the range of f of x equals the square root of x minus 5, all of that plus 1. For x in the reals, no, for x in the reals greater than 5. Greater than or equal to 5. Alright, now we know that the range of the square root function is the set of non-negative reals, but we are adding 1 to this function, and therefore the range is all reals greater than or equal to 1. State the range of f mapping x to 2 to the x, where x is a real. Okay. So, 2 to the x. What does it look like? It's an exponential, so it grows incredibly rapidly in the first quadrant, and in the second quadrant it approaches but never touches the x-axis. So the range is the set of all non-negative reals. The range of f is the set of non-negative reals. Section 2.3, composite functions. Given that f of x is equal to x squared and g of x is equal to 2x add 3, find f of g of 4. So first we find g of 4, which is 2 times 4 add 3, which is 7, and then we find f of 7, which is 49. So if f of x is equal to x squared and g of x is equal to 2x add 3, then f of g of 4 is equal to 7. 49 rather, 49. Hello. Oh, no. That was read the wrong way around. Alright, let's self-correct. If f of x is equal to 2x add 3 and g of x is equal to x squared, what is f of g of 4? First we must square 4 to get 16, and then we must do 2 times 16 add 3 to get 35. If f of x is equal to 2x add 3 and g of x is equal to x squared, what is g of f of 1? First we have to find f of 1, which is 2 times 1 add 3, which is 5. And then we need to find g of 5, which is 5 squared, which is 25. So if f of x is equal to 2x add 3 and g of x is equal to x squared, then g of f of 1 is 25. If f of x is equal to 3x minus 2 and g of x is equal to x squared, then solve f of g of x equals 25. So if g of x is equal to x squared, then f of g of x is equal to 3x squared minus 2. And if 3x squared minus 2 is equal to 25, then 3x squared is equal to 27, and x squared is equal to 9, and thus x is equal to plus or minus 3. So just to reiterate, if f of x is equal to 3x minus 2 and g of x is equal to x squared, and f of g of x is equal to 25, then x is equal to plus or minus 3. Given that h of x is equal to 1 over x for non-zero x, and h of x is equal to 7, find x. Well, this function composed with itself should just be the identity function, as the reciprocal of the reciprocal is itself, and thus x should be 7. Given that f of x equals x minus 4 and g of x is equal to the square root of f, find the domain of g of f of x. Alright. So we need to substitute x minus 4 into the square root of x. So we have the square root of x minus 4. That's their composite. And the domain of that is the set of reals greater than or equal to 4. Next, inverse functions. Given that f of x is equal to 3x minus 7, find inverse f of x. Okay, so the usual strategy is to say that y is equal to 3x minus 7 and then to solve for x and then replace y with x, and then you will have your inverse function. So if y is equal to 3x minus 7, then y plus 7 equals 3x, and y plus 7 all over 3 is equal to x. So inverse f of x equals x plus 3, x plus 7 all over 3, x plus 7 all over 3. So if f of x is equal to 3x plus 7, then inverse f of x is equal to beg your pardon? Oh. If f of x is equal to 3x minus 7, then inverse f of x is equal to x plus 7 all over 3. Given that f of x is equal to x add 2 all over x minus 1, and f is self-inverse, find inverse f of 5. Oh, beg your pardon, I missed a bit out. Let me repeat. Given that f of x is equal to x plus 2 all over x minus 1, where x is not allowed to be equal to 1, and it's self-inverse, what is inverse f of 5? As it's self-inverse, we need to only substitute x equals 5, and thus we have 5 add 2 over 5 take 1, which is 7 over 4. Given f of x equals x squared plus 1, try again. Given f of x equals x squared plus 1, and x is greater than or equal to 0, find inverse f of 10. So, we set up the equation, 10 equals x squared add 1. So 9 equals x squared. Then it's tempting to say x is plus or minus 3. However, it has been said that x is greater than or equal to 0. Thus, x is equal to 3. Given f of x equals e to the 2x for real x, find inverse f of 1. We form the equation 1 is equal to 2x. Then we know that 2x is equal to 0, and thus x is equal to 0 itself. A one-to-one function satisfies f of 3 equals 8. Find the corresponding point on inverse f of x. Okay, if f of 3 is equal to 8, then inverse f of 8 is equal to 3. Section 2.5, y equals the modulus of f of x, and y equals f of the modulus of x. State the coordinates of the vertex of y equals the modulus of x minus 3. Now for y equals the modulus of x, the coordinates of the vertex is the origin. As we are subtracting 3 from the argument, it undergoes a horizontal transformation of 3 units to the right, and thus the new vertex becomes 3, 0. How many solutions does the modulus of x squared minus 4 equals 3 have? Now, for the modulus of x squared, we visualize the standard parabola passing through the origins, the standard unit parabola passing through the origin, opening upwards. For x squared minus 4, that unit parabola is translated 4 units downwards. For the modulus of x squared minus 4, the part below the x-axis gets reflected up into the first and second quadrants over the x-axis. And then we have to answer the question, when is it equal to 3? Well, visually, we can see that the local maximum would be 0, 4. That would be the vertex. No, hold on just a second now. Yes, that would be the new vertex of this function. And thus we can see four possible routes. So we're going to see if we can find them. So we're going to say x squared minus 4 is equal to 3. And in doing so, we get plus or minus root 7. But then we have the other ones. So we're going to say x squared minus 4 is equal to minus 3, in which case x squared would equal 1. In which case x is plus or minus 1. So it's plus or minus 1 and plus or minus root 7. Given f of x equals x minus 2, state the range. Not getting it right. Let me try again. Given f of x is equal to x minus 2, state the range of y equals f of the modulus of x. Alright, so we can visualize f of x equals x minus 2 as just simply y minus x, but translated downwards by 2 units. Now we need to think about y equals f of the modulus of x. Alright, so just let's do it 1 second. Alright, so the effect of that would be what would the effect of that be? The effect of that would be that the part of the graph that is strictly in the third quadrant would sort of like get reflected up somehow, but there's no efficient way to describe it. But anyway, alright. I've actually forgotten the original question. Okay, if f of x is equal to x minus 2, find the range of y equals f of the modulus of x. The new vertex, or the new minimum, would indeed be 0. No, it would output, the vertex would be 0, negative 2. And so the range would be the reals greater than or equal to negative 2. State the y-intercept of y equals the modulus of 2x minus 6. So 2x minus 6 is a straight line graph with a gradient of 2 and a y-intercept of negative 6. But then we're finding the modulus of it. Alright, and then we have to also find the range of it. So the range of it should simply be the reals, the non-negative reals. Hey, sorry, yes, is it asking that? No, it's not. Okay, restart. Find the y-intercept of y equals the modulus of 2x minus 6. Alright, so the ordinary linear function y equals 2x minus 6 has a y-intercept of negative 6. But we're finding the modulus of this, the absolute value. So the answer to that is 6. The curve y equals f of x has minimum point 1, negative 9. State the corresponding point in y equals modulus of f of x. Alright, so it forces that point over the x-axis. So instead of being 1, negative 9, it would be 1, 9. Section 2.6, combining transformations. The point 2, 5 lies on y equals f of x. Find its corresponding image in y equals 2 times f of x plus 3. Alright. So the effect of adding 3 to the argument is that the entire function is translated left by 3. And then the effect of multiplying by 2, multiplying the function by 2, is that the entire function, the graph of the function, is stretched vertically by a factor of 2. So what happens to 2, 5? Well, it's translated 3 to the left, so it becomes negative 1, 5. And then it moves vertically to a point twice as far away from the x-axis. So it becomes negative 1, 10. So I believe that negative 1, 10 is the image of 2, 5 under the function transformation y equals 2 times f of x plus 3. The point 6, 4 lies on y equals f of x. Find its corresponding image in y equals f of 2x all take 1. So f of 2x means that 6, 4 has the image of 3, 4. But then by subtracting 1, 3, 4 will move to 3, 3. So I believe that 3, 3 is the image of 6, 4 under the function transformation y equals 2 times f of x all take 1. The point 1, -3 lies on y equals f of x. Find its image in y equals 3 minus f of x. Yep. All right, let me try again. Okay. The point 1, -3 lies on y equals f of x. Find its image in y equals 3 minus f of x. So for the minus in front of the function moves 1, -3. Across the x-axis into 1, 3, and then the plus 3 moves it to 1, 6. 1, 6. So I believe that 1, 6 is the image of 1, -3 after the function transformation y equals 3 minus f of x. State the translation vector mapping y equals x squared onto y equals all of x minus 4 squared plus 1. Okay, so subtracting 4 from the argument translates the function 4 units to the right, but then adding 1 to the entire function translates the function 1 unit upwards. And therefore the translation vector should be 4 on top, 1 on the bottom. The curve y equals f of x has asymptote x equals 2. State the asymptote of y equals f of x plus 5. Adding 5 to the argument of the function translates the function leftwards by 5 units, and thus x equals 2 should also move leftwards by 5 units, and thus it becomes x equals -3. Right, last section here. Solving modulus problems. The modulus of 2x take 1 equals the modulus the modulus of 2x take 1 equals the modulus of x add 4. All right. the modulus of 2x take 1 equals the modulus of x add 4. The modulus of 2x take 1 equals the modulus of x add 4. So solving ordinarily, 2x take 1 equals x add 4. Thus x would be 5. But I think that there should be some other solution here, but I can't see it. Let's try and push a little bit harder. Right, there must be some way to do this. Right, I'm struggling to see how it's not just simply negative 5. No, I do see. Right, I see that now. Yep, I see that. All right, okay, so we're going to make one of them negative then. So we're going to say minus 2x plus 1 equals x plus 4. So 3x equals minus 3, so x is equal to minus 1. Yeah, so I think that 3 and negative 1 both work. Solve the modulus of x minus 2 is less than 5. All right. So y equals x moves 2 downwards. But then the modulus means that it reflects on the 2. But then we have to say when it's less than 5. Right, so that should be true when x is less than 3, but also what? Alright, so just translating this here. Okay. Alright, so that's peeking out. Alright, so that's been a good session.